In the last decade, we have achieved a lot. From shaping the human evolutionary timeline to discovering new genetic engineering techniques and detecting gravitational waves. It has been one hell of a decade for science. One of the most recent and more prominent achievements from the 2010s was photographing a black hole. But not just any black hole, we photographed Messier 87, a black hole located in the heart of its galaxy, millions of light years away. In this video, we will uncover exactly how we achieved this, and detail the incredible journey traversed by the light lucky enough to escape the force of a black hole. We will also explore the challenges that we faced and how we overcame them all for one photograph. Our journey starts 50 million years ago. Electromagnetic radiation released from the black hole with wavelengths no longer than 1.3 millimeters, also known as radio waves, are capable of escaping the violent nature of a black hole. They then must propagate for 60,000 years to escape their own galaxy, encountering various obstacles, many of which could absorb them. Once free from their own galaxy, they then must continue for 50 million years, travelling through the empty void to reach our own galaxy. A key challenge we faced when attempting to take such a photograph was the diffraction limit. To overcome this, the team needed a telescope the size of Earth. However, with this being impractical, a virtual telescope was created. This virtual telescope would use interferometry. To do this, the EHT would use a network comprised of 8 telescopes. The telescopes made use of the Earth's rotation to fill in the coverage gaps. The result was a virtual telescope with a huge resolving power. To put it into perspective, it was described as being capable of allowing an observer in Washington to be able to read the date on a coin in Los Angeles. These telescopes would then use the Fourier Transform, a process that allowed the telescopes to break down the black hole's brightness patterns. Given that the telescope relied on radio waves, EHT operated telescopes that were at higher altitudes. This is because the atmosphere has less particles, such as water vapor, that could affect the quality of the signals. Each observation took many hours. Like when photographing a dim object with a regular DSLR, the longer the exposure, the more detail that could be resolved. The result? A lot of data. 5 petabytes of data. So much data that it was faster to transport the data via aircraft as opposed to transferring it digitally. Once EHT had collected all the data and had compiled it, the result was this: a blurry orange blob that precisely matched predictions made by computer simulations. The bright region is where plasma jets are emitted at its poles. These jets are beams of ionized matter that are accelerated to near light speed. We assume they are the result of extremely strong magnetic fields and are channeled away from the black hole as a result of its rotation. As a result of its near light speed, the jet facing towards is brighter, whilst the jet pointed away is dimmer. This is caused by relativistic beaming. This same phenomenon explains why we can see the jet facing towards us, but not the one facing away, in this photograph taken by the Hubble. This may seem confusing, but rest assured that we will cover these complex topics in future videos. We now know from this observation that the jets have an orbit time of 2 days, and they extend for over 5,000 light years. M87 also has a mass equivalent of 500 million solar masses. And that dark region at the centre, that's its shadow. Close to a light day in diameter, it is casted by the event horizon, often referred to as the point of no return. It is so large that you could almost fit the entire solar system in there. So that's that. We'll be sure to link any resources below if you're interested in further reading. We're always open to feedback or questions. Feel free to leave them in the comments. All details and links will be in the description as well. Thank you.